If you've ever had a dental filling, you know the drill. The dentist puts in the filling material, and then they grab that little wand with a bright blue light to make it hard. It seems like magic, right? Almost instant. But what if I told you that in that first second, and maybe for many seconds after, absolutely nothing is happening at the bottom of that filling? Today, we're diving into that hidden delay.
So the big question is this: does a filling really start hardening the instant the blue light turns on? We all assume it does. It makes sense, right? Light on, reaction starts. But this entire explainer is based on a fantastic piece of research that throws a huge wrench in that assumption. And you'll see, it could totally change how we think about one of the most common procedures in all of dentistry.
You know, in the dental world today, speed is everything. We all want to get in and out of that chair as fast as possible. And that demand has led to some pretty amazing tech. Super high-power curing lights that promise a rock-solid filling in just 1 to 3 seconds. Now, the whole idea behind these super-fast cures rests on a principle called exposure reciprocity. It's pretty simple, really. It just means if you crank up the power of the light, you can proportionally cut down the time you shine it. But you gotta wonder, does that simple math actually hold up in those first few absolutely critical seconds?
Well, to figure that out, we have to get into the chemistry of it all. And it turns out, the hardening reaction doesn't just fire up on command. Before any of those resin molecules can start linking together to form a solid, they first have to get over a pretty major chemical hurdle.
And that hurdle has a name: polymerization inhibitors. These are tiny molecules, including plain old oxygen, that are mixed into the dental resin on purpose. Their job is to keep the material from hardening in the tube, to give it a good shelf life. The thing is, they work a little too well. When that blue light finally hits them, all its initial energy has to be spent just getting rid of these inhibitors.
Think about it like boiling a pot of water. You can turn the stove on full blast, but the water doesn't instantly become steam, right? First, all that heat energy has to go into getting the water up to 100 degrees Celsius. It's the exact same idea here. The light's energy is first spent creating these little sacrificial molecules that go out and consume all the inhibitors. Only after that job is done can the real hardening actually begin.
Okay, so if this delay has always existed, how come we're just learning about it now? Well, the answer is pretty simple. Previous experiments just weren't fast enough. Their equipment couldn't see what was happening in that first fraction of a second. It's like they thought the race started when the gun went off, because they couldn't see that the runners were still stuck in the starting blocks.
And this is where the real breakthrough of this study comes in. The researchers used a high-speed technique that let them take about 13 measurements every single second. That is incredibly fast. We're talking a new data point every 77 milliseconds. And that speed, that high resolution, is what finally let them see what was really happening in those first critical moments.
And with that powerful new tool, the results were totally unambiguous. Every single material they tested, at every thickness, showed a very real, very measurable time delay before the hardening even started at the bottom of the resin.
So how long are we talking? Well, get a load of this. For a pretty standard resin, at a common filling depth of 4 millimeters, and using a lower power light, the delay was almost 16 seconds. For 16 seconds, that blue light was on, but absolutely no hardening was happening at the bottom of the filling. Zero.
Okay, what's so fascinating here is just how predictable this delay is. You can clearly see two things. One, the more powerful the light, the shorter the delay. That makes total sense. But two, look at the difference between the materials. Even with a high-power light, one resin still has a delay over 2.5 seconds, while the other is down to just a fraction of a second. This tells us the delay is a dance between both the light and the specific chemistry of the filling material.
And this is where it becomes really, really important for the dentist. Let's go back to that popular 3-second high-power cure. We just saw that for a 4 millimeter deep filling with this NeoSpectra material, the delay was 2.69 seconds. That means for almost 90% of the recommended cure time, nothing is happening at the bottom. The effective curing time isn't 3 seconds, it's just a tiny sliver of a second.
All of this leads to a really powerful statement from the study. Because the light hits the top surface first, the top gets over its inhibitor hurdle and starts to harden while the bottom is still stuck in that delay. The takeaway is huge. The bottom of the filling literally cannot bond to the tooth until well after the top has already become a solid.
So what does this all mean? Well, the implications are pretty big. First, those super short exposure times could leave the bottom of a filling totally uncured and unbonded. Second, this time gap between the top and bottom hardening might actually explain why tiny gaps sometimes form at the base of a filling.
And for the scientists, it means that a whole lot of past research that just assumed the reaction started at time 0 might need a second look.
This leaves us with a pretty fundamental question, doesn't it? If the curing clock doesn't start ticking when the light's turned on, then when does it start? This research forces us to totally rethink how we define the beginning of a successful cure and how we can make sure we're accounting for this invisible but absolutely critical delay.
This work is a perfect example of how looking closer and measuring faster can completely change our understanding of a procedure we thought we knew inside and out. To really dig into the data for yourself, scan this QR code to get free access to the article.